Alright, so in this video we're going to take a look at some simulations investigating how current and resistance are related to one another. So just to quickly give a little background here. So when we talk about resistance in an electric circuit, it's the degree to which a component resists a current passing through it. So if we have the same potential difference applied across a range of components, if you get a small current, we describe that component as having high resistance. If we get a big current, we describe that component as having low resistance. So if we have the same potential difference, resistance allows us to tell what's going on with the current. So in terms of how we actually calculate resistance, resistance is defined as potential difference divided by current. So it's V over I. So first of all, we're going to look at how we can figure out the resistance of a component. So the first thing we're going to do is build ourselves a circuit that looks a little bit like this by opening this link. So here we go. If we open up this lab, I'm going to quickly pause this while I build it because it's a little bit fiddly. Okay, so here's our circuit. You can see we've got our power source, we've got an ammeter to measure the current going through our resistor, and a voltmeter to measure the potential difference across the resistor there. So we've been able to build the circuit that we've been asked for here. So what we want to do is change the battery EMF to a range of different values and record the potential difference across the resistor and the current passing through it. So to start off with, I've got it set to 9 volts, and we can see we've got a current of 0.9 and a potential difference of 9.00. And that's 0.90, so making sure we're getting the correct precision on our data. I'll calculate the resistance values in a second. So let's change this, and it doesn't really matter what we change it to, so let's go 19. So you notice the potential difference across here is also 19, because it's the only component in the circuit. So all of the energy gets lost between here and here. And we've now got a current of 1.9. You might be noticing a pattern here already. Let's just plug ourselves another random one. 43.50, giving us a current of 4.35. You should definitely starting to notice a pattern now. Let's get one sort of in between. Yes, this one's 36.5. And the current is amazing, 3.65. And let's pick one final one. So we've got a good set of data. Let's give ourselves a low one as well. So we've got 2 and 0.20. And so one of the things I would draw your attention to with this table is a lot of people get really stressed about the fact that their potential differences aren't increasing and they're not increasing in equal intervals. So you can see I've tried to get a range of potential differences, which would be useful in terms of our data, but having them in order and having fixed intervals is just not very important. Okay, so let's now calculate our resistances. So we're going to do potential difference divided by current, which gives us 10. And I'm expressing it as 10, not 10.0, because this 0.9 is a 2 significant figure number. This next one is also 10, but I would express it as 10.0, because this 1.90 is 3 significant figures. This is 4, so we should give it to 3. 10.0, 10.0, and 10.0. There. Oh, hang on. That shouldn't be a 0.0. This is only a 2 significant figure number, so therefore that should only be 10. Okay, so here is our data. So you'll notice the resistance is exactly the same, 10 ohms, for any of these potential difference readings. So in terms of what we noticed, let's make this bold. Okay, so you can see that the resistance remains exactly the same regardless of the potential difference or current. So this is what we find for a fixed resistor. There are other components like diodes, light bulbs and things where that wouldn't be true, but this one is true for a fixed resistor. And the relationship we can see is what we'd call a directly proportional relationship. Okay, so that's what I'm seeing. It's directly proportional. And in terms of the evidence for that, the evidence is that the ratio of potential difference, and what that means is potential difference divided by current is the same. Okay, so we handily calculated that and we call it the resistance. But so this is what this resistance is. It's the ratio of potential difference to current, and it's the same for all of them. So that is evidence for being directly proportional. Alternatively, you could phrase this as doubling potential difference causes current to double. Either of those two things is evidence for a direct proportional relationship. If we plotted them on a graph, the fact it's a straight line through 0, 0 would also be evidence for directly proportional. So any one of these pieces of evidence is absolutely fine, depending on how you approached it. Okay, so let's move on to experiment 2, where we need a different simulation. No, I don't want to close that. So we want to look at resistance on a wire. We want to put all three variables up to their highest setting. Okay, and so you can see with everything on high, so we've made resistivity, which we're not really going to go into in this video. We don't really come across this much until we get to A-level kind of A. We've put length to maximum, 20 centimeters, and we've put area to 15 centimeters squared. So when we talk about length, we're talking about how long the wire is here. So you can see I can change that, make it really short, make it really long. And with cross-sectional area, we're basically changing how thick the wire is here. Okay, so we put them all to maximum. Now we're going to investigate how length and cross-section area affect resistance, but keep other variables the same. So first one I'm going to do is the length. So we can see with length, we've got, these are all bold, which I don't like. So with 20 centimeters, you can see we've got a resistance of 1.33. Let's do a few different lengths. Oh, I'm never going to get exactly 15, so let's not waste time trying to do that. Let's do about 10. Yeah, that's close enough. 10.14, 0.676. So what I'm noticing already is we've halved the length, and you'll notice the resistance is halved. So it's looking like a directly proportional relationship. Let's do 7.14. That's 0.476, and let's do a low one as well. And we've got 3.67. And we do 0.245. Now you might be wondering, how would we actually practically measure these resistance values? And we do it exactly the same way we did here. So what we'd actually be doing is measuring the potential difference and the current, and we'd be dividing those two, and that would be where these resistance values actually come from. Obviously the length measurements we'd get just with a ruler. Okay, so that's how length and resistance affect one another. Actually, let's draw a conclusion before we do anything. So I'm seeing a directly proportional relationship between length and resistance, and the evidence for that is that and you can see that in this table here. So when length is 20 and it's halved to about 10, resistance halves as well there. Now let's do the same thing for cross-sectional area. Let's put length back up to its maximum. So in here we've got, I hope you managed to spot the correction in the table. So our area is 15, resistance is 1.33. Let's get rid of the bold straight away. Boom, 12.85. And you'll see I'm really not paying attention to making these nice values or anything like that. We've got 2.08. Now I'm going to try and get about 7.5 here, which is half of 15, which will be a useful one to have in our data set. I won't be too picky, but I would like to be a little bit closer. There we go, 7.46, perfect. 2.68, and let's do one smallish one. Okay, and the final one, 3.51, and we can see that's 5.70. So things I'm looking for, so here we have halved the cross-sectional area, and what you should see is that resistance is actually doubled. So that's characteristic of an inversely proportional relationship between cross-sectional area resistance. And the evidence for that is that when halves the resistance actually doubles. So that's why it's inverse, not direct proportional. Because direct proportional, if we double one, we double the other. With inversely proportional, if we double one, we end up halving the other. So they have different characteristics there. And so you'll notice when I was doing these experiments, I was very careful to have a result which was half, or in here, and the same thing in this one here. So then it makes it easy to spot these kinds of relationships when you're doing the experiment. So in terms of the final one, so we've got these summary questions. So if you were to apply a fixed potential difference across a conductor, if you increase its cross-sectional area, what would be the effect on current you'd be measuring through it? So the first thing I would say is that resistance and current are inversely proportional. Okay, so basically if we've got a fixed potential difference, resistance and current are inversely proportional. So if resistance increases, current decreases by the same factor. So for example, e.g. doubling causes to halve. So but the factor here is 2. So if we multiply resistance by 2, we cause current to be divided by 2. So increase area, resistance decreases, and therefore current increases there. So if we have a bigger cross-sectional area, we expect current to be bigger. And if you think about it, if you have a wider wire, if you think of it like a pipe, if you have a wider pipe, you can get more water through it every second. So a wider wire means we can get more charged particles through it every second. That stands to logical reasoning there. And if we do the same thing with length and current, so increasing length causes resistance to increase. So increasing length has the effect of decreasing the current that's going through a wire. And the rational reasoning for this is the longer the conductor is, the more collisions your charged particles are kind of having as they pass through. So they end up actually moving slower, which means we can get fewer charged particles through that conductor every second there. And there is this final section looking at resistivity, but I'll leave you to explore that one on your own if you so choose.